All right. So what did we do last time? Constraint optimization. Essentially, it was so this was your constraint set. All we did was, and this was, let's say, your point xk. We took the gradient descent direction, and then whatever point we reached, we projected it back and called it xk plus 1. So this is one way of doing things. Suppose you want to go from, you want to solve a constraint problem using unconstrained optimization. What are possible ways? So think of minimizing f of x subject to, let's say, g of x less than equal to 0. One way is to do this. Okay. Consider this as your constraint set, repeatedly keep doing projection. That's one way of doing it. Instead, what do I want to do is, I want to somehow construct a method which will repeatedly solve some unconstrained problems to get an answer for the constraint. So I'm not going to repeatedly project it back. So it will so this is artificial in some sense. You're artificially forcing every step to go back to x. Is there a natural way where whatever you do will naturally make sure that the solution ends up in x? So what could possibly you do? At least the idea is not that difficult. Analysis, one can see how to make it work.
So you want to fall inside the chi set, right?
Look at the problem I want to solve. Minimize f of x such that x is such that g of x is less than equal to 0. So what kind of unconstrained problem I can potentially solve so that when I stop, I can say more or less I'm at the right point.
You have done that. So you can look at the indicator set, multiplying the f with the indicator of.
But that's in some sense impractical. That's essentially rewriting the problem. That's not really solving the problem. I could always rewrite f of x plus indicator g of x less than equal to 0. That becomes an unconstrained problem, but doesn't help me. How do I solve such a problem? So I can always move the constraint into the objective function by just saying plus an indicator, where indicator is special type. It's 0 whenever its g of x is less than equal to 0, infinity outside. It makes it even non-differentiable. So any methods you've been using will potentially fail. Think about something more natural. It should be natural to think about that. Okay. What is the rationale behind? It's a good direction. Okay. Yes. Okay. So what should happen?
So as I keep taking bigger and bigger lambda, it should remain at 0.
Okay. So how should I? So also tell me how to choose lambda. So why are you even doing this incrementally? Why not just choose an arbitrary large lambda one time?
Sorry, could you just repeat the whole question?
Question is sitting there.
Yeah, but like so.
I want to repeatedly solve unconstrained problems, and I want to try to solve this problem. That's very simple.
Last time we did.
No, last time we did this. It repeatedly projected it back.
Yeah. So that's why you are constraint set.
Sorry.
Last time we wanted to solve a constraint set. And you want to solve the constant for the unconstrained.
Why are we confusing? My question is very simple. There's nothing to be confused about. I want you to think about a method which only involves solving unconstrained problems to solve this problem. As simple as that. So what you're saying is fine. How do you actually do this is somewhat cumbersome. How should I select? And why should I do it even repeatedly? Why not just select arbitrary large lambda? Do it once.
Because whatever the lambda we select,
Yes.
there could be function states.
Correct. So now what do I do?
Keep incrementing lambda. Maybe take double
Every time. Okay. What do you think is going to happen? Why are we doubling it? Why are we not taking a principled approach with respect to finding the right lambda? I'm not saying that's the method I'm going to discuss today, but that's a reasonable method, what we are saying. What are they trying to say? Instead of the constraint, I'll think about the following potential. All right. Now this is unconstrained for a fixed lambda. Okay. Now suppose I pick a large enough lambda and solve it once. What can you say about that problem and this problem? Can you always guarantee feasibility is the question? Not necessary. Whatever lambda you pick, I can create a function such that it's not necessary that the object, the optimizer here is such that g of x is less than or equal to 0. Not necessary. But there are ways to come around that. And did we talk about primal dual methods? There was a primal, there was a dual. This is precisely, lambda is nothing but a dual. So you should actually can do this as well. So what you do, I'm not going to discuss this today. So you do both update x and lambda. So for x, you do gradient descent. For lambda, you do gradient ascent. On exactly this Lagrangian. This is nothing but Lagrangian. On this, the x domain, so fix a lambda, do a gradient descent step. Fix an x, do a gradient descent, a gradient ascent on lambda. I keep doing this alternatively. This is a potentially correct approach. But this is a complete different class than what I'm going to talk about today. So any other idea instead of, so what you did was essentially looked at a Lagrangian. Any other idea which does not involve Lagrangian directly? Okay, so given that I'm regularly running over time, let me just do this. Okay, so let's define what is called as a penalty function. So function P from Rn to R is called penalty function if one g of x is 0 when g of x is less than or equal to 0. Okay. And 2 very simple definition. Okay. So give me an example, anybody? Any example for penalty function?
Distance from the set where gx is equals to 0.
There's nothing left for distance. G of x is inside it.
For the so we have a set for g of x less equals to 0.
Yeah.
So what I'm doing, so it's calling that set x,
Okay.
and I am looking at,
But I want an example.
yeah, distance function from distance function x comma the set x.
Okay. Fine.
So when it is gx is less equals to 0.
Fine. One example. Another example. So you're implicitly assuming that the set you're talking about is a convex set. I've not said anything about that. You'll be in trouble as soon as distance, you start talking about distance if the set defining g of x is not convex. Any other function which comes to mind? Something much simpler.
So you have examples for both for G and T.
No, g is given to you. You don't have to worry about what g. Given a g, what is a valid p? G is given to you. G is some fixed function. Because this is not contingent on particular g. For any g, I'm defining this. So you give me g, I will output a p.
Gx plus the essential maximum 0.
So example, p of x is equal to max of 0 comma g of x. That's what you want. Okay, does it work? It works. Right? There are many other things. Typically, what people end up using is a square on that. But any power p is okay. Any other example which comes to mind? So dot dot dot. This is not unique. Okay. So what we really after is to minimize f of x subject to g of x less than 0. What are we going to do? We're going to rewrite. Let's call it minimize f of x plus c times p of x. And let's call this function u of x comma c. All right? And now this is unconstrained. So this is what I want to solve.
Okay, so the penalty function, you don't require any, like it might be continuous or something, anything.
For the moment, I've said nothing. Definition doesn't require anything. When it comes to proving something, then we need something.
So, okay.
The definition doesn't require it to be continuous. The theorem we'll prove will require P to be continuous. Is it clear what we're doing? This is the problem I want to solve. Here is the problem I'm actually going to solve. Now, can you tell me, suppose I do it for a fixed C. Is it at all useful or should I do something? Or you can prescribe an procedure of selecting C. Is the method clear? What is going on? P is nothing but a penalty function. C is some constant. If I do it once, what do I get? Do I get anything interesting? I get an x, which is a function of C. So what is an immediate observation you can make? That as C decreases, something interesting is going to happen, or as C increases, something interesting is going to happen.
So the E is a penalty function.
P is penalty
Yeah,
function.
if there's a constant C, we increase, that means the penalty on the function is increasing.
Because of the multiplier increasing. P of x is not changing. P of x is P of x. Yes.
And if we try to decrease C,
Yes.
the penalty is going to decrease.
Correct.
So, but we want, so if we want to make C decreasing, then we will actually going towards our main problem, that is the minimum of the minimum of x of fx, where constant is gs less equals to 0.
No, it's opposite. What problem I'm solving? Solving a minimization problem, right? And as C increases, what is happening? What is the incentive for the optimizer? To go
Outside is very, it will be very fine.
exactly. So if C is large, there is a heavy penalty for being outside. So the optimizer automatically will try to push towards the constraint side. That's the big picture. So that if I can solve this problem repeatedly by increasing C, I should expect myself until some technical conditions to reach the optimizer of my original problem. That's the basic picture. It's not very different from the Lagrangian, except that the P of x is not G of x directly. That's all. That's the only change we really made. So the penalty function is positive outside, not zero inside, essentially. That's all has really happened. You don't need differentiability. All you essentially what we're going to prove, as long as f and p are continuous, we'll get what we want. But the idea should be clear. What are we trying to do? We're repeatedly going to solve this by successively increasing C. And it doesn't matter how you increase, as long as the limit goes to infinity. That's all will matter. You don't need to double all the time. Just this, the sequence CK should just go to infinity. That's all. But is the big picture clear? What are we trying to do? No. So the condition we'll need on C is that sequence CK is such that CK plus 1 is greater than CK and limit CK goes to infinity. That's all we'll need on CKs. And the theorem we are going to prove is the following. The theorem. Suppose f of x, g of x, and p of x are continuous. No mention of any convexity anywhere. And the algorithm here is, so xk is argmin q of x comma ck. That's my algorithm. It's clear? This is the algorithm. Every time I plant a ck and find the optimizer. So let xk be the sequence of optimizers. Then any limit point of xk solves the original constraint. So, which is this. So let's call this script P. All right. So what do I need to show if such a claim has to be made, that the limit of xk or the limit point is feasible and its value is at most the optimal value of my program script B. Both need to be satisfied. Right? So far, so good. Very like hardly any assumptions or technical. All we are asking is F, G, and P to be continuous. But the requirement here is that I'm asking you to find xk to be exactly the minimum point. So that you should take into account. How am I going to do this? That's your problem. As long as you can do that, this theorem will guarantee that you're reaching a constraint optimizer. Any questions? So this is a key step. For convex functions, it's easy. Non-convex functions slightly harder. But as long as you can do that, you're fine. Even if it is non-unique, I think is okay. Okay. So some elementary properties of this, so let's call them proposition. 4 of them really. Proposition. 1. Function xk ck is less than equal to q of xk plus 1 keep in mind what is q of xk ck. F of xk plus ck p of xk. That's sure. Okay, so why is this true? We want to prove this. This is the definition of Q. So let's write it x of k plus 1, comma, ck plus. What is it by definition? Just that f of xk plus 1 plus ck plus 1. Okay. What can you say about this? What is the property of the sequence? Ck plus 1 compared to ck? So this is greater than equal to f of xk plus 1 plus ck p of xk plus 1. You can make it strict also, it's not a problem. All right, what more can I say? And what is by definition xk? It's argmin of f of x plus ck p of x. That's the definition of x of k. Can you use that somewhere? By this definition, I want to go to q of xk ck, right?
But that is this equals to x.
Is that true? Let's call this 1. Because this is the optimizer, so any other point, the valuation has to be larger. And what is this term? It is nothing but q of xk. Question? As I said, all these the 4 propositions I'm going to write, all of them are elementary. That's the beauty about this proof. There's hardly anything non-trivial. You just have to repeatedly use equation number 1. So this monotonicity we have established with function Q. What about P? What is the relation between P of xk and P of xk plus 1? Even if you don't have an answer, think about it. What should happen for an algorithm which is doing the right thing? Yeah, why? Exactly. If your algorithm is doing the right thing, the penalty should decrease. Okay, so now how do we prove that? It's in fact true. Definition of P of xk is clear, right? Xk is this. P of xk is nothing but evaluation of this on P. Everything is on the board, whatever you need. Think about for a second. How would you like to prove that P of xk and P of xk plus 1 have a interesting relationship? All you have to use is equation number 1. That's all you have to use because there is nothing more available to you. From equation 1, what do we get? Superposition number 2. I'll write the statement later. That f of xk plus ck p of xk is less than equal to what? F of xk plus 1 plus ck p of xk plus 1. This is from 1, right? That's all. Xk is a minimizer for a fixed value of ck. So ck is common every. So that's why this is true. But there is nothing special about ck. I can do the same thing with xk plus 1 plus ck plus 1. P of xk plus 1. And now this should be less than equal to what? Now you get the wind, I guess. See, xk plus 1 is a minimizer when I plant ck plus 1. So this should be less than equal to any other value, including f of xk plus ck plus 1 p of xk. Again, using 1. Now look at 2 and 3. Do you see something which you can use? All we want to understand is relationship between p of xk and p of xk plus 1. That's all we want to understand. So what can you eliminate from here? Can you eliminate all the f's?
Yes, by adding.
Adding or subtracting? You need subtraction. Move this that side and just add these two inequalities. So this is a minus f of xk when you move it there. And this is a plus. Similarly, this is minus of f of xk plus 1 and there is a plus. If you add these two inequalities, what do you end up getting? Something to do with something like this. Or ck plus 1 minus ck times p of xk is greater. Signs have been switched because that's why ck became ck plus 1 minus ck times p of xk. This is identical, so this cancels off, and also is non-zero because ck plus 1 is strictly larger than ck. So I get p of xk to be greater than equal to p of xk plus 1. Again, elementary. So now tell me the relationship between f of xk and f of xk plus 1. Doing incrementally. We looked at q, next we looked at p, now we're looking at f. Now what should happen? It should increase. Why? Because p is decreasing. Sorry?
Q is increasing and P is decreasing.
Exactly. If you just put essentially 1 and 2 together, what will happen? Q is increasing while P is decreasing. F is nothing but a difference of the two. So I should get that. So you can put the. And what about the most interesting? F of x star. So x star is my optimizer of the original problem. What can I compare this with respect to Q of ck xk? I wrote it wrong. Sorry. F of xk. I want a question mark here and a question mark here. Question?
Actually, now I'm not sure about that.
Okay, why are you not sure?
Because we saw that P is decreasing, but CP.
CK is increasing. CK is increasing.
Yeah, CK is increasing and P is decreasing.
Yes.
So we don't know the difference between Q and CP.
Okay. So who wants to attempt a proof? Go to the definition. That's all.
Q is increasing, first of all. And Q is increasing.
Yeah.
Uh,
Q has CK involved already.
yeah. So since if PK is decreasing and CK, you don't know that which is the rate of decreasing is higher or increasing higher. So essentially, to make it strong, like even if the CK is decreasing slower, increasing slower, then the way PK is decreasing, and PK should decrease faster. Like,
We have not established any of that.
but PK should decrease faster. We want that.
Not needed. That's the whole point. If you just use equation number 1, it's enough. So by 1 again, what do you get? This is true from 1. No. Can you finish the proof? I want this. Just making sure. Third one, yeah. This we know.
Yes.
Can you use that to finish the proof?
Since P is decreasing, right?
Yes. So this term
So
and this term have a relationship from 2 for a fixed CK. His doubt was this is going to come up with a different pairing, but that's not going to spoil the party because of equation number 1, that xk is the local minimizer with respect to ck. So given, so now this is less, this implies that f of xk is less than equal to f of xk plus 1 from proposition 2. All right. Now let's look at the number 4. All less than equal to. Okay. Let's put tentatively. So which one you can prove
Okay.
We'll fix it. Let's see if it works or not. So first tell me why do you think it's less than equal to, and then we'll try to prove. So forget for the moment this. What would you think should be a relationship between f of x star and f of xk? That's q of thing is a artificial quantity. F of xk and f of x star.
Limit.
No, for any xk. This statement I want to write for any xk.
X star is the minimizer.
X star is the minima of the original problem, constraint origin. Script T.
We put any point except x star, it will be that it naturally higher than the minimizer.
So you think this should be the correct direction? What you're saying is, suppose this was not there. You're saying f of x star should be less than equal to f of xk. Is that what you're saying? Don't hesitate. If you're saying that, you say, yeah, say okay. Is anybody who wants to refute that? Do you think it's right? That's an obvious answer what you're giving. But now think for a second.
That is only true if g of xk is less than equals to u.
Okay.
Otherwise, it might be that like f of xk could be smaller than f of x star.
You see the point? That xk for the moment has not shown to be feasible. In the feasible set, x star is the optimizer, not outside.
Taken xk is the argument of those.
So I've just looked at a penalty function. I've not done anything. We're not ensuring that xk, otherwise you're going back to solving the constraint problem. Solving an unconstrained problem every time to find x of k. Right? So again, use one. We'll put the, let me erase this for the moment. What does one tell you? It's amazing that all four things are coming from just this simple definition of xk being the optimizer. Okay. What does one tell you? F of xk plus ck p of xk is less than equal to f of x star plus ck p of x star. This is true for every unconstrained problem, right? So this is definitely true. What can you deduce?
So in the x star,
Yeah.
we want the parent to be higher than any.
What? By definition, x star is feasible. P of any feasible point is 0. So this is at most what is this quantity? This thing is positive. So I can go to the left of it and say this is in fact true. But what is this? So I get everything I want. Like make a hash of it. Yeah. So just essentially one necessary condition for xk to be optimal gives you everything. So all four propositions are done. Now we are ready for proving the theorem. Just to go back to the theorem, what do you want to prove? Fx, gx, and px are continuous. Ck is such that the limit ck goes to infinity, ck is increasing. Xk is argument of this, then xk converges. So the limit point of xk goes to the optimizer of. So now what do I need to show something like this? What should limit point do? Essentially, I want to show that limit point is optimal. Right? So what should I do to show that? I need two things, right? The limit point should be feasible, and f of the limit point should be less than equal to f of the limit point. Limit point should be feasible, right? That's the first condition. And f of the limit point should be less than equal to f of x star. Then I'm done. Or equal to, whatever. If you can show less than equal to is fine. Because by definition, it can't be smaller. So it has to be equal. So who wants to attempt? Again, the proof is elementary. So think of a limit point. Why does it have to be feasible?
G is continuous.
Given f, g, and p, all are continuous.
Yes. So G is continuous and xk is also feasible. That is.
xk feasible? We never showed anything of that type.
xk is just equal to optimize.
Yeah. Unconstrained optimize. But you proved some proposition 1, 2, 3, 4. If they are not useful, you would not have proved anything.
So x star is greater than or equal to f of xk.
Yes, that's what you show.
But
We were saying the last inequality was all greater or equal to same, right? So if we can show for some particular k that we are taking any of the reverse inequality.
Those are all the propositions we need. Nothing more is needed.
Okay, so if we can show it, so you know that k is increasing.
Fk is increasing. We proved something. Yes.
Yeah,
F of xk.
f of xk is increasing, right? And it is bounded above by f of x star. The last proposition,
Okay.
right?
Mm-hmm.
And
Okay,
q of x is also increasing,
Q is also increasing.
and it is bounded above by f of x star. So it has subsequential limit
You
onward.
don't need all that. You can keep going down the path you're going. You don't need subsequence and all.
So it's bounded sequence.
It's monotone. So it's
Yeah, no, so if you converge
Mhm.
a point.
But you already taken the limit point.
Yeah.
And functions are continuous. Why can't you directly use that? You're on the right path, just finish it. You proved something special about 1, 2, 3, 4, the propositions. Maybe I should just.
Continuous function, I stick more continuous function, right? So in more continuous function, it will convert to the upper bound.
Okay.
Because at most
Okay. Yeah, it's not necessary if you go there. Right?
so we have to show that that is least of all.
No, but yeah. What are you trying to like? Forget about math. What are you trying to show? That x, the limit point is x star.
Yes.
Okay.
No, if I can show that
That's too much to ask for.
multiple points.
What you should be asking is, am I feasible? Is my limit point feasible? That's the first thing you should ask yourself. And then you'll worry about what is the function valuation at that limit point. So why do you think your limit point is feasible? What gives you that? The only control is via the penalty function. So all you have to show is that the P of the limit point is 0 somehow. You don't have direct control over G. All we are playing around with is P. We've thrown away, forgotten essentially G. So whatever the limit point of these iterates is,
Is also continuous.
G is continuous, yes,
But the penalty is continuous.
yes.
Penalty is decreasing.
So no, I'm saying what you need to show to claim that you are feasible is the P of the limit point is 0. That will imply that G of limit point is also less than or equal to 0 and feasible.
That is so P is the penalty is continuous function. It's more on decreasing. More on increasing function.
Which function?
The P side.
What was the definition of P? We didn't say any of that. Where is it monotone increasing and all? All it said is this is greater than 0 whenever G of x is greater than 0. I didn't say anything about that.
If the limit point is not feasible,
Mhm.
then the function Q diverges to infinity.
How does one see that? Is there a quick argument?
Yeah, because at the limit point, we take the C goes to infinity and
Ck goes to infinity, yes.
CK goes to infinity. So f of limit point is constant. P of limit point.
F of limit point is constant. F of limit point is what? Why is that not going to infinity? Because it is upper bounded. Okay.
And P of limit point is, since it is not a feasible solution, it is something positive.
Yes. So it should go to infinity. While it is bounded by f of x star, which is bounded. We'll do something very similar. Is it clear? No, don't come up with your own. What are we trying to do? We're trying to somehow show that the limit point of the sequence has a property that P of that limit point is 0, which will imply that it is feasible. Now, why should it be 0? We have shown f of x to be upper bounded. We've also shown the whole function to be upper bounded. And these ck's are going to infinity. Now, how is it possible that this is not going to 0? This is going to infinity. This is bounded. For all of this to be bounded. That's not possible. So this better be 0. That's the whole big picture. That's why ck going to infinity is important. Okay. So proof. Let x bar be the limit point of xk. So what is limit k going to infinity? F of xk. What is this equal to? F of x bar. Why? When is this true? So f is continuous by our assertion, by assumption. Since f is continuous. Now let's look at limit k going to infinity q of xk comma ck. What can I say about this quantity? And let's define this to be q star. From my proposition number 4, what do I get? That this is less than or equal to f of x star. Right? Now, what is limit of ck p of xk? By definition, is nothing but q of xk ck minus f of xk. Limit of that, just by definition. Where ck I'm missing. Where should I put ck? Oh. That's it. This is the definition. By definition, Q of xk ck was this term plus f of xk. So I've just rewritten that. So what is this equal to? Q star by definition minus how much? So far, so good. Now, what do I know about CKs? They are going to infinity. Okay. Given that CK is going to infinity, what can you conclude from all this? Is everybody convinced?
The Q star and X star is constant.
Q star is what? Upper bounded by f of x star. What is f of x bar?
The limit of and function.
Yeah. So why is the information that CK going to infinity tell me something about the sequence P of xk? I want to conclude something about the limit of P of xk. Why is it 0?
If it is not zero, like Q star minus f of x star is bounded.
Okay.
But
CK is going to infinity. So how can it be bounded if unless P of xk goes to 0? There is no other way. So P of xk has to be limit of P of xk goes to 0. Or implies limit of P of xk 0. Okay. Is that sufficient to claim that x bar is P of x bar is 0? That's what you want, right?
x star is a limited point of P is continuous.
P is continuous, G is continuous. So this implies that P of x bar is 0, which implies that x bar is 0. So continuity of all three is required. Okay. So at least x bar is feasible. Now what about f of x bar compared to f of x star?
Because f of x k is increasing to at least like f of x bar is less than f of x star. F of x k is increasing and
See, this term is true for every f of, what was our lemma? F of xk is less than equal to fx star for all xk. So that is also true for the limit point. So by proposition 4, f of xk is less than equal to fx star. Therefore, we get f of x bar is also equal to f of x star. Therefore, x bar is what? Any comments? Elementary proof. Simple idea. This is called the penalty method of solving constraint problems. Here, every problem you're solving is unconstrained. The next thing we'll discuss is the barrier method, which is, so this was essentially you're given this constraint set, you just threw it out. All you did was you created a surrogate function for yourself, which is P of x, which was 0 in the feasible set and non-zero outside. That's all. And by making sure that the sequence CK is increasing, you're naturally pushing your objective function towards the constraints. And in the limit, it gets you to the right.
This same for multiple constraints.
Yeah, that's why I didn't do this. You can do it with as many constraints as you want. I just kept it simple so that notationally it makes it easy. As long as your penalty function satisfies that relationship. Because it's nothing but the intersection of, if you put more constraints, the constraint set is nothing but intersection of all of them. That's all. Now the method we'll look at is called as barrier method, interior point method. Many names it goes by. It's very famous also. There you insist that you are inside this boundary, and then you're playing from the inside towards the right answer. Here you didn't respect that. You just went outside anywhere you liked, and then you tried to converge towards the optimum. Here somehow we want to maintain that from the inside we'll get to the right answer. So it's slightly tricky compared to this method, but it has
In the interior, it will be non-zero and outside it is zero.
no. So there's a
As approaching toward the boundary, it will be zero.
the penalty function. What did it do? It looked at the constraint set, put a value 0 inside and a non-zero value outside. The barrier function is a barrier. Think of this as a really a Lakshman Rekha of some sort. But suppose this is your constraint. To the left, you don't want to go. Everything to the right is fine. Now, if you're somehow the constraint is moving or an algorithm is moving towards the boundary, what do you want to happen? Somehow, you should give it sufficient resistance that it pushes back. One way to do that is to come up with a function which just very rapidly increases as you approach the boundary. That's why it's called barrier method. It tries to push it back naturally, not by saying, if you go out, I'll project you back. As you come closer to the boundary, the function itself, which we will add to the objective function, will explode. So that will never allow you to actually go outside.
Okay, so from approaching
From the inside. Will not even define from the outside.
Okay, so approaching from starting from interior point, as you are going anywhere towards the boundary, the function should explode to infinity.
Yes. But if it ends up that the optimal value is outside, also very close to the boundary, there should be some way of compensating for that. So that's what this method is. Does both the jobs simultaneously. So what do? So you look at your constraint set S. Domain of this barrier function is S minus, which is the interior of S. Right? On this interior, the function should, as it gets to the boundary, it should go to infinity. That's really what you want. So, can you give me an example? 1 by g of x. Will it work? Right. Now, what is the special property of this? On the outside, it's not necessarily infinity. But as it gets closer to the boundary, it just keeps increasing. That's why it's very weird.
So basically, then your algorithm should start from
Inside and stay inside, that you have to
how
ensure.
you know? Because last day when we did the
So there are ways to do that also. So we haven't discussed that, but that's possible.
no, but if there is a way, then we could have chosen the same trick for the last day's method in the project too. And starting with the point.
Inside, yeah, you can start inside.
You said that getting a point, feasible point inside on
That itself is a convex problem.
yes,
But there are ways to do that also. It's not infeasible. But that is a problem to be solved. Yeah. But that doesn't, so for the projected gradient descent, even if I give you a point inside, that doesn't mean it's optimal. You still have to follow the method. It's only a feasible point. So here, supposing, let's call it b of x to be equal to this. It has a weird behavior. As you get closer to the boundary from the inside, it gets to infinity. But once it goes over, it comes back to something bounded. So something which remains infinity everywhere, what can that function look like? That's typically the function used, but the definition, this is valid. So think of a function which as soon as it approaches boundary or goes outside, always is infinity. Indicator is bad, right? You don't want indicators. Yeah, indicators are, because otherwise I could just plant the so every constraint problem can be solved as an indicator problem. So log barrier. Log is a nice function. What should I put inside the log? Minus g of x or g of x?
G is negative. Oh, G is the
So minus g of x will make sure done. So this is called a log barrier. Most useful or most used rather barrier function is the log barrier. So everything else is in the same spirit as what we did is the penalty method, except now. So remember what problem we're trying to solve? Trying to solve minimize f of x subject to g of x less than 0. In the penalty method, what did we do? We moved to minimize f of x plus some ck p of x. The barrier method, the only difference is because we have defined this barrier only over the interior, we'll solve this problem. So minimize x belongs to s minus f of xk plus ck b of. There should be no k here. Alright. So the only difference is it's not completely unconstrained. You somehow to ensure that what you're doing is it remains within the boundary because the function is not even defined outside. It turns out that there are ways to get away from this for special functions. For arbitrary functions for which I'm trying to prove, somehow you have to ensure this. If you have what is called a self-concordant barrier, you can get back. So for the moment, assume that you can do this. Yes.
So, one thing, getting like if you want a barrier function like infinitely differentiable, that will might be
I don't understand. Say it again.
getting a barrier function that is infinitely differentiable.
Infinitely differentiable. We didn't even ask for it.
I'm just asking that.
Yeah.
Rather than asking for that, if we go for.
But where did I ask for it?
If we look at maximization of minus f and look take a bound function, C infinity bound function, that is always rather useful to get one.
I don't follow what you're saying.
So if we work with max of minus f,
Yes.
and if we just take a bump function inside,
What is the bump function?
like it will be approaching 0 towards the boundary, and C infinity function.
I have no clue what is C infinity function. Why are you asking such things? It's not also not clear. In the definition of my barrier function, I have not asked for even continuity. The definition of barrier function is clear. That it should explode at the boundary. If not written down, I'll write everything down. Nothing more is being asked. For the moment, not even continuity. The theorem will prove will require that the function be continuous. The barrier function, all that I'm asking is from the inside, as you approach the boundary, it should explode. That's all I'm asking. Nothing more. Is that okay? Differentiability is far away. We're not even asking for continuity. The point I'm trying to raise is in the penalty method, we didn't have to do anything with respect to over what domain we are trying to optimize. Here, given that the barrier function is only defined for the domain, you are by default constrained to lie there. So that's a small distinction. But this theory works because there are ways to avoid that. So when you're solving a linear program in your favorite solver, it's actually solving this. So Karmarkar became so much famous because of this. There are ways to avoid solving that any constraint problem. You can do completely unconstrained and still get to the right answer. Simplex, everybody read simplex? Simplex is too complicated for solving linear programs. This is what is used to actually solve linear programs. Okay, so now let's go to the definition. Oh, is that b of x. So typically the boundary is defined as dou of s. So as it approach the boundary, b of x explodes. That's all your definition. You can make it slightly stronger here to say, yeah, let's not make it bounded. It's not bounded. It's fine. Sorry? S minus belongs to, sorry.
Minus in the interior.
Interior, yeah. And now you repeatedly solve. Repeatedly solve the problem. Minimize x belongs to s minus f of x plus ck b of x. So now what should the behavior of ck should be? Should it increase or should it decrease?
B of x is blowing up.
B of x is blowing up. So what should happen to C of? Now we're inside.
So we're trying to make it fall. Want CK to fall to have a lower and lower value actually, because BX is blowing up
Yes,
and CK is also
increasing. What will happen? It will never allow you
Yeah.
to even go too close to the boundary. So ck is a decreasing sequence. So ck is greater than ck plus 1 and limit ck is 0. That's what you. So this is the basic barrier method. Now, given your special functions, you can do something interesting to avoid this minimizing over a constraint set. You'll automatically be, without doing this, you'll be automatically guaranteed to stay within. That's the whole point. You still want this to happen, but without enforcing it. Okay, so the theorem. This requires an extra technical condition that we write it from the book. It's better here. What is the technical condition? You don't need whatever I'm giving you is sufficient. I know that these books are super costly, so I'm not expecting you to read these books. Don't worry about that. There's too much material in this book. As long as you absorb the concepts, you should be fine. Okay. So let S minus be non-empty, first of all. And that any feasible point that is not in S, that is not in S. That means it's on the boundary. See, all of S is the constraint set. I've extracted the interior and calling it S minus. So any point which is not in the interior but feasible.
Then it's not in S minus.
Yeah, any feasible point that is not in S can be approached closely. So this is the loose term. We'll write exactly what it means. Closely from S minus. So in particular, what that means, given any x belongs to S and any delta greater than 0, there exists an x tilde belongs to S minus such that x minus x delta is less than equal to. That's all we need. We should be able to approach any point on the boundary from S essentially. That's all it means. So given any x belongs to S, see if x belongs to S minus, then it is x tilde equal to x itself. It's only for points which are not in S minus. That's really what we're after. Question? Which one? Let's forget for the moment. We'll correct that. So as long as this we understand, we can correct. So take any point which is in S. If it's in S minus, all of this is trivial. So take a point which is not in S minus, but in S. Take any delta greater than 0. I should be able to find an x tilde in the interior so that the distance between them is less than that. Now tell me what the mistake is.
It is not an S minus that will approach closely from S.
It is not in S minus. Yes. Which one?
Closely from S.
No, from S.
X.
No, that is correct. That you're within and you're able to approach. Should maybe make it.
Usually the size, like the shape, not convex, it doesn't matter.
No, so this is to avoid pathological conditions. So if your S is x such that g of x is less than 0 and g is convex, this is always true. It's only to avoid weird, because we're not making assumptions about g and f's and nothing. That's why
I'm saying that suppose your convex is very like flat.
as long as g is convex, this is always true. The claim we are making is for arbitrary functions. That's why you have to avoid certain pathologies.
A very basic doubt of mine, but if we have a point on the boundary, then by definition it will be the case that any ball around that point will also have a point that is in the intersection of. Like,
so yeah, go back and think. If it was always true, one wouldn't need this. So yeah, so it's not always easy to construct things that is it always true or not. So it will require a thought that is it always true or not. And it's not true, that is why you need all such. So it's not easy for me to construct you one example where that is not the case.
But like the definition of a part of the boundary is that it must lie in the closure. It must lie in the closure, but not in the interior. Right? Like,
so yeah, so there are some.
If you are thinking about R&D,
Yeah, so this is to avoid all possibilities. What kind of topologies we want to put? I don't know.
think about it R&D.
okay.
So things can be super complicated.
Okay.
Yeah. So don't just think in. It's what you're saying is possibly true for whatever example you had, but that doesn't mean that it's true always. So, yeah. But for any nice enough set, this is true. So don't worry about that. The problem you will look at will not satisfy that. But it's universally true. That might be complicated. I don't have a ready example where it's not true.
You can create something in T1.
Topology, all sorts of things happen.
Yeah.
That's why we are worried.
T1 space. Look at it.
Have you come across Banach-Tarski's theorem? So that's your bottom line. Most non-trivial of things will be true in life. It's like impossible to think, right? You break something and you put it together and increase the volume. What is going on? Similarly, another example which is difficult to construct is a non-measurable set. In your probability class, take a homework for yourself. Create a set which is not measurable.
We did that using an axiom of choice. Then.
You did it already.
And there is only one example.
Yeah.
This
Just exactly.
In our department, probability 1 and probability 2 is overlap, not trivially, in a higher group.
No. So if you have one example, try to create another and see how difficult it is to actually come up with that. So certain things are not easy to see why you need it. Once you have it, it's easy to prove something. That's the point. And for most things, you will have this condition true. Of course, for G is convex, it's true.
We're not dealing, this is not just in some metric space.
Yeah, this is most general. The theorem I'm proving today is the most general. We're not assuming anything on F, G, B, nothing. We're making it very general. When you simplify or specialize it to convex things, or rather the way the barrier method is used, as I said, this also goes away. You'll be automatically guaranteed that whatever you do unconstrained will remain in S minus.
Okay, so just sorry once again.
Yeah, go ahead.
Some topology.
Yeah, just to avoid getting stuck, because I need something from here to prove. It's not true that if I don't have it, I don't have the result. Just it's easy to prove the result when such a condition is there. Okay, so what is the theorem? Let F, G, and B be continuous. Then, under the technical condition, the limit point A sequence is an optimal solution. The theorem statement is more or less identical. All I need is this extra technical condition. What is this xk? Xk is this sequence, which is repeatedly solving. So xk is nothing but argmin of this. That's all. So I will just indicate what the technical condition gives you. Rest of the proof is identical. We proved the same 4 propositions, identical to before. All that I need is the following. So the technical condition guarantees the following. For any epsilon greater than 0, there exists an x tilde such that gx tilde is less than 0 and fx tilde is less than equal to fx star plus an epsilon. That's all you really get from the technical condition. Rest you prove identical relationships to my 4 propositions and complete the proof. There's nothing really going on. This is what you get from the technical condition using the continuity of f and g. I'll post these notes anyway, so if you want to really look at it, the proof is not different. So what are those 4 propositions? We'll state. So similar to before, let's call R of xk ck to be f of xk plus ck d of xk. Right? So proposition number 1 is R of xk ck is greater than equal to. Now ck's are decreasing, so you get all the reverse signs. That Remember CK, the decreasing sequence. Something is not clear?
Looking at the further.
Okay, so what does it mean? Essentially, you have this constraint set. That's what it means, that x tilde is in the constraint set, g of x tilde less than 0. What is it guaranteeing? That f of x tilde is at most f of x star plus epsilon. So essentially, even if it's very close to the boundary, such a thing happens. If it's x star is far away from the boundary, it's automatically true. It's only when it's very close to the boundary, still I have something to approximate, is what it's telling you.
So like x tilde and x star are two different points, but the optimal value is almost same. That's what it.
I can approximate, I can reach, that the whole point is I can reach. Yeah. And f is continuous, so that's why it gives you that. So the first is this, then you get b of xk is less than equal to b of xk plus. Essentially, everything is going in the opposite direction. F of xk is greater than f of xk plus 1 and 4. Where is my 4?
In the third one, we didn't really need to have S.
Yes.
In the case of penalty functions.
There was no s.
Yeah, so that's why you will have to face this condition.
Yeah, of course. We just threw away everything. We didn't care about domain, interior, nothing. We just threw the set away, got a surrogate function for ourselves, which was 0 and non-zero. That's all. X star is an equal of xk. That's all. So once you have this, you can complete the proof. There's nothing really going on. This is all. These are also 4 very elementary. So if you put, let's call it equation number 5 plus these 4 gives you the answer. And today I will finish on time. All right. So we're almost close to what I wanted to cover in the whole course. I will see if there is anything missing. One thing which is missing, and I promised to in the flyer, was something called online convex optimization. So next Wednesday, depending on, Monday is a holiday. So online convex. This looks like somewhat of a magic that one can actually do this, but one can do it well, and the proofs are very simple. So I'll just give you a flavor of what it means here. There are many other things in the Boyd's book as well, which you would like to cover. So beyond the course, there is something called equality constrained. I think chapter number 9 in Boyd's book, state optimization. What it really does there is takes the Newton's method and adapts it to allow a constraint of this type, Ax equal to b. So the Newton's method we studied in the class was unconstrained. But even if you have a constraint of this type, it can be adapted directly. So whenever you have time beyond the course, you can go back and read that. Yeah, Ax equal to b. Equality constraints of this type, because that's all he really understands. That's how a convex problem is even defined. For equality, it has to be X equal to b. That's our vanilla definition of a complex problem. For inequality, any other function is fine. But equality only so. So g of x less than equal to 0, where g is convex. But for equality, you needed Ax equal to b. So Newton's method can be easily adapted even when there is an equality constraint. So that's one thing which I did not cover in the class. I think you can read it yourself. There's another class of functions which are, maybe that's what I will cover next time, called self-concordant. And this really comes to help you when you're applying the interior point methods. So this is some, I don't want to define it today, relationship between the third derivative. Now suddenly third derivative pops up for the first time. So far we only looked at second derivatives. This is the first time you see third derivative. And it suddenly helps you to avoid solving this problem, which is constraint. So once you have work with self-concordant barrier functions, you don't have to do the constraint optimization here. That's the power of it. So most likely I'll cover that. If time permitting, I'll just give you a definition of online convex. Otherwise, next semester. All right, let's stop here.